Okay, so in the last class we were talking about one-dimensional motion of particle through a fluid, right? Okay, so what we did was we kind of came up with a governing equation that basically describes, when a particle is moving in a fluid, but that's in one dimension. Such a case, I mean, as we were discussing, it could be a simple, if you take a case where if you have a column of liquid, say that the liquid in the column is stagnant, and if you have a particle that is moving under the influence of an external force, so we basically set up a working equation, right? And that working equation looked something like this, right? A times E into rho p minus rho divided by rho p, right? Was it rho p or rho p, right? Okay, minus CD into AP into rho v square by 2 times m was equal to dv by dt, right? That's the working equation, right? Everybody knows how to get this, right? Now, as I was saying, this equation is a general equation which is valid for particle of any shape, right? And for any fluid particle combinations, right? Now, if you want to simplify this further, before we do that, I said that as soon as the particle is dropped into the column, what will happen is you'll start with the particle being at rest. Okay, now once you drop it, it's going to accelerate, right? And then this acceleration is going to die down soon because of the fact that there's a drag force that is acting on the particle, and ultimately the particle will start moving with a constant velocity, right? Okay, so at some point in time your acceleration is going to be zero. Okay, that's because the particle is going to reach a constant velocity, and you can get that constant velocity as I mentioned in the previous class. It is denoted by ut, or the terminal velocity. People also call it as terminal settling velocity, and that we obtained it as some a times E into rho p minus rho divided by rho p into 2 times m, right, divided by CD AP into rho under square root. Okay, right? That's what we had developed. Okay, now if you want to simplify this further, I was mentioning that you would have to. So of course we talked about two different cases, right? One, I can say that AE is the acceleration because of the external force. Okay, it could be working with any external force that you wish. Okay, but if you take a simple case of external force being gravity, okay, we said your AE is going to be G, which is the acceleration due to gravity. And of course, if you take your acceleration, if your external force is like say centrifugal force, okay, you're going to replace that AE with R omega square, right? So now, if you want to simplify this further, we said that we should know what is the CD, right? If you look at the equation here, right, rho p is the property of the particle, rho is the fluid, okay, AP is, so there are certain parameters which depend on the fluid, and there are certain parameters that depend on the fluid that you are considering, right? Now if you want to simplify this further, we said that you would have to go back and look up things like this. Okay, this is an example where what is plotted is the drag coefficient CD on the y-axis versus Reynolds number on the x-axis, right? If you look at this plot, there are kind of two limiting cases. Okay, one is in the low Reynolds number regime. Okay, when the Reynolds number is less than 1, okay, your CD versus Reynolds number can be represented by an empirical equation, which is something like CD is equal to 24 divided by Reynolds number. Okay, I can simplify the expression that we just wrote for the Stokes law settling regime. And if you look at the high Reynolds number regime, when your Reynolds number is more than 1000 up to about 200,000, your drag coefficient more or less remains constant, right? Typically about 0.44. Therefore, what I can do is I can actually substitute for these things in the working equation. So what I'm going to do is simplify this. Okay, so let's so therefore your ut, okay, was if I take AE to be G, right? So it was 2 times M times G into rho P minus rho divided by CD AP into rho under square root, right? That was the, did I miss something? I have rho P as well. Okay, right? So now what I can do is, you have M here, right? And you have rho P here. I can replace that with Vp, which is the volume of the particle, right? And I also have CD, which, sorry, AP, which is, as I said, it's a projected area, which is pi dp square by 4. Okay, and CD, as we have been saying, this is CD is 24 divided by particle Reynolds number, or REP or NREP. Therefore, that is 24 divided by dp ut rho divided by mu, right? Where mu is the viscosity of the fluid. So if you put in this, okay, we can do that quickly. So therefore, your ut is going to be 2 times, instead of m divided by rho p, I'm going to put it as pi dp q by 6, right? That's your volume, right? Multiplied by, I have G rho p minus rho divided by, I have CD here, so I'm going to write it as okay, let's do for AP first. AP is going to be, I'm going to have 4 in the numerator, it's pi dp square, that's for AP, right? And I also have rho here. Now for Reynolds number, it's going to be I'm going to multiply by mu divided by 24 times dp ut into rho, right? That's your mistake. So your CD is 24 divided by Reynolds number, right? So that's going to be dp v bar rho by mu. That's going to be, that's right? So therefore, I can cancel these two here, and I can cancel. Okay, I think I've done a mistake, right? This is going to be, oops. It's going to be dp here into ut here into rho divided by mu, right? Yeah. So then you have dp square here, and there's dp power 4, so this is going to be dp square will come in the numerator. So you have 4 here, and there's going to be 6, right? Therefore there's 1 here, 3 here. Okay, so therefore basically if you work it out, and of course your rho and rho is going to get cancelled. Okay, therefore if you work it out, it turns out that your ut is going to be g into dp square into rho p minus rho divided by 18 mu, because 3 times 6 is 18, and you're going to have mu in the denominator, and your numerator is going to be g dp square into rho p minus rho. Okay, you can work this out. Okay, this is the working equation if you have, like, say, a particle which is settling in the Stokes regime. Okay, Stokes regime is basically if you have your particle Reynolds number is less than 1, your ut is going to be g into dp square into rho p minus rho divided by 18 mu. Okay, now similarly, if you work out for Reynolds number, that is greater than 1000 but less than 200,000. Okay, in that case your CD is going to be constant, and that is 0.44. Okay, if you substitute for CD in the expression for UT, and then if you simplify it further, what you would do is you would get UT as 1.75 into square root of G into rho P minus rho into dP divided by rho. Okay, you can work this out at home. Okay, therefore these are the two limiting cases for the settling of particles in a fluid. Okay, the expressions for the terminal velocities, which are applicable for the limiting cases. One, for when the Reynolds number is less than 1, this is what is called as a Stokes settling regime. Okay, other for cases where the Reynolds number is in between 1000 and 200,000 is something called as a Newton's settling regime. Okay, now, so of course these are applicable for spherical particles, right? Because that's what we considered in this case, pi dP square by 4 being substituted for AP, which is the projected area, which is only true for spherical particle, right? So therefore, if you have other objects of other sizes, okay, so it turns out that so if you want to generalize for particles of any shape, what you should do is you should have some correlations like this. Okay, what you're seeing in the plot is again CD versus Reynolds number, but if you look it up, there are different plots. Okay, there's one plot for cylinders. For the spherical particles, it's a continuous line, right? The continuous line is for the spherical particles, which we just saw, right? The two limiting cases of CD being 0.44 or CD being 24 by Reynolds number. And the other two are for particles of different shapes. Okay, one is for disks, other one is for cylinders, and these have been generated by taking particles of particular dimension and particular shape, and they have been held in some particular condition. For example, in this case, axis of the cylinder and face of the disc are perpendicular to the flow direction. Okay, if you have a liquid that is flowing, the axis is in a direction perpendicular to the flow. Okay, that's like this. Okay, therefore, when you want to work out the equation for settling velocities for different shaped particles, you would have to worry about the orientation of the particle as well. Okay, whether the particle is oriented in the direction or in the direction perpendicular to the flow. Okay, when the particle is oriented perpendicular, it's something called as a bluff body. Okay, that's a terminology that people use, okay, in the literature. So therefore, I would have to take care of such issues when you want to simplify these equations for calculating settling velocities for different shaped objects. Now, okay, if you're given a problem that say that a problem is given to you and you want and they want you to calculate what is the settling velocity of the particles. Okay, now how would you go about doing this? So say that there's a problem that is given. I can say that, hey, there's a particle of 100 micrometer diameter. It is settling in a liquid column. Say that the column is filled with water. I'll give the density of the liquid, water, and then also the viscosity of the fluid. And if you were to ask to calculate what is the settling velocity of the particle, how would you go about doing the calculations? So one crude way of doing this would be you calculate your UT, okay, for the Stokes regime. Okay, get what is your UT, okay, and then from that you basically calculate what is the Reynolds number. After that, I have done the settling velocity calculations. You assume that UT is, say, G dP square into rho P minus rho divided by 18 mu. You calculate the settling velocity, then you get UT, then you back calculate what is your Reynolds number. Okay, if it is d, okay, ut by mu, right? If the Reynolds number falls less than 1, then I say that, whatever I assume that the particle is settling in the Stokes regime is correct. Okay, therefore my assumption is right. Okay, but that need not be the case all the time, right? You can end up with a Reynolds number which could be more than 1, it could be more than 1,000. So therefore you kind of come up with a kind of an dilemma as to whether I should be using the Stokes regime or the settling regime or the Newton's regime. Okay, so therefore what you can do is you can come up with a simple non-dimensional number, okay, which can help us in terms of identifying the settling regime without going into this guesswork. Okay, I said that the guesswork is you assume that the particle is settling in the Stokes regime, you calculate ut, back calculate your Reynolds number, see whether it's less than 1 or look at the typical range or typical number that you get out of the calculation, and then if that's not the case, then you go back and then assume the Newton's regime, and then again calculate ut, calculate again Reynolds number, right? So instead of doing that, what you can do is you can rearrange the expression that you have for your settling velocities, right? I know that ut is g dp square into rho p minus rho divided by 18 mu for the Stokes regime. Okay, I know that my Reynolds number, okay, for the upper limit of the Reynolds number for Stokes regime is 1, right? Anything less than 1 is a, so now what I can do is I can substitute dp into rho into ut divided by mu. I can substitute for ut from the Stokes regime. So what do you get? Sorry. Okay, that's going to be your g dp square into rho p minus rho divided by 18 mu, right? So what I can write this as, so this is going to be, I'm going to write it as q. Okay, ouch. Okay, and I'm going to write this as 1 over 1 divided by 18, right? Now let's look at the exact similar formulation for so we know that your Reynolds number should be more than 1,000 for the Newton settling regime. So similarly, I can write the Reynolds number as dp into rho by mu into 1.75, right, square root of g into rho p minus rho into dp divided by rho, right? That's your expression for the. So now what I can do is I can take the dp inside, right? So I can write as dp cube, right? I'm going to take, is that okay? Okay, and then I have rho here. Again, I'm going to take rho square inside. I'm going to write as rho square. Okay, and of course there's going to be mu square as well, right? Okay, so now I'm going to cancel a few things, right? So that's going to be there's one mu goes, right? And what else do I have? Okay, but I've forgotten. Yeah, so that should be okay. So did I do a mistake here? No, right? 18. Oh, there's going to be mu square here, right? Yeah, right? Okay. So look at the term that is in the, okay, there's g here, right? There's dp cube here. There's rho p minus rho. Did I cancel one of the, what's the expression for the Stokes settling regime? I made a mistake, right? There's no, there is no. So what we did is right? dp into rho was in the numerator. Okay, that's going to be rho square here. So can you help me out? So I have 1.75. Okay, let me just write it. So here is 1.75 into square root of g into rho p minus rho into dp divided by rho, right? That's my Reynolds number. So you're okay, there's going to be rho square here, and there's going to be rho here, so therefore that seems okay. Oh yeah, so it's okay, right? So I think that's fine. So I have a row here, right? I have a row here, g here, right? dp cube rho p minus rho mu square. Is it okay? Therefore, I can actually define a factor k. Okay, I can define a factor k as g dp cube into rho p minus rho into rho here divided by mu square to the power of 1/3, right? So therefore, this is going to be 1/18 into k cube. Okay, and here it's going to be 1.75. Okay, again into k cube to the power of 1.5. Is it okay? Is it okay? So therefore, from the just by rearranging the two expressions that we had, one for the Stokes settling regime, another one for the Newton settling regime, what we have been able to do is we've been able to get 1/18 into k cube is equal to 1 is the case for Stokes settling regime. Okay, and 1.75 into k to the power of 1.5 is equal to 1000 for the Newton's settling regime. Okay, if you work it out, in this case your k comes to be something like 2.6. Okay, if I k cube is 18, okay, therefore k is going to be cube root of 18, so that's going to be 2.6. okay, and similarly the k for the Newton's settling regime comes out to be something like 68.9. Okay, 68.9 if I substitute the lower limit of the Reynolds number for the Newton's regime, and if I substitute the higher limit of the Reynolds number, which is 200,000, your k comes out to be something like 2360. Okay, therefore, okay, the idea is this. Okay, so what you do is you calculate the k, okay, which is basically defined as g dp cube into rho p minus rho into rho divided by mu to the power of 1/3. You calculate that. If the value of the k that you obtain, if it is less than 2.6, okay, then you use the settling velocity for the Stokes regime and calculate your terminal velocities. Okay, however, if the k factor that you're getting, if it is between 68.9 and 2360, okay, that's the range of Reynolds number over which the settling occurs in the turbulent condition, that is the Newton settling regime. Okay, in such case you would have to use the appropriate expression for the terminal velocity for the particle in the Newton's regime. Okay, so therefore this formalism, okay, in terms of calculating k, okay, as a criteria for deciding whether I should go for a Stokes or the Newton's settling regime is useful, okay, instead of doing a guesswork of assuming a particular settling regime and then back calculating your Reynolds number. Okay, any questions? Do you have any questions with this? Okay, it was just a manipulation, right? It was just a rearranging of the expression for each of these UTs, and then equating that to the limiting value of the Reynolds number for respective conditions. Okay, that's all we've done. Yeah. Okay, so yeah, so now we'll talk a little bit about before we talk about applications of these things. Okay, so now what you see is a plot, okay, of variation of settling velocity with size. Okay, on the y-axis you have terminal velocity. On the x-axis you have equivalent spherical diameter. Okay, and there are different curves, right? One to they're numbered from 1 to 9. Okay, and they have taken different fluids. For example, 3 is aniline, 7 is nitrobenzene. Okay, so basically what we are looking at is a case of fall of liquid drops in water. Okay, so far when we looked at settling, we only talked about solid particles, right? We talked about spherical particles, rigid, hard particles. Now if you were to plot terminal velocity as a function of size of the particle, okay, it would always be a monotonically increasing function, right? Because in the case of Stoke settling, your ut goes as dp square, right? And in the case of Newton's settling regime, it goes as dp to the power of half, right? So therefore in both the cases, as I increase the size, my settling velocity should always go on increasing, right? That means it's a monotonically increasing function. Okay, now if you look at this plot, okay, can you see some difference? Okay, the first difference which is very apparent is that it looks like the settling velocity increases, okay, in analogy with what is known, okay, for smaller dimension. For example, maybe in the range from 0.0 to 0.6, okay, in that centimeter size range, the terminal velocity increases with size. However, it attains a maxima and it basically drops back, right? Okay, so any thoughts as to why that could be the case? So everybody understand the plot, right? It's a plot of terminal velocity is a function of equivalent spherical diameter. So why does equivalent spherical, why is it not the diameter of the drop? Why is it a equivalent spherical diameter? Okay, the obvious answer is going to be because the drop, right? The drops can also change the shape. So therefore, when one is dealing with drops in a fluid, I would have to worry about shape changes. Okay, that means depending upon, so the reason why it would go to a maximum and then drop off, because one naive answer could be that in the initial, for the smaller size regime, the droplets will remain spherical. Okay, however, when you make the droplets bigger and bigger, at some point they're going to flatten, right? They're going to flatten, and then your drag is going to be more. Okay, more drag means it's going to settle slower, right? So anyway, we can think of, we'll argue a little bit along these lines in a minute. This is again some data again for, so I don't know if you noticed this, right? This is a paper from IIT Kharagpur, which is published in 1950s. Okay, so people were worrying about settling of droplets and other stuff then itself, right? Because it's, and again the settling of drops in a fluid is also relevant to one of the common thing that you guys see. An example, raindrops, right? Okay, when the rain falls, right, these are going to be water droplets. Okay, as they approach Earth, they're going to again flatten in the direction of the gravity, right? So in depending upon the size of the droplets that are going to be generated, okay, if the size of the droplets are very very small, then you can assume the drops to be spherical in shape. Okay, they would come like a hard sphere. However, if there's a larger raindrop, the moment it exceeds a particular size, if I were to go by this plot for like say 4, which is some carbon disulfide, okay, there's a peak, right? I can draw a vertical line, and I can actually get what is the limiting size for which the droplet behaves like a sphere. But beyond that line, where you see the drop in the terminal velocity, that's when the shape change would have occurred. Okay. Again, there are more data. This is again from some other paper. Again, the characteristic peak in the terminal velocity followed by a decrease is evident here as well. Any thoughts as to why the 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 other nice things to notice is the peak, where the appearance of the peak, right, seems to be shifting towards smaller sizes, right? If I look at the bottommost plot, which is for aniline, right, or the topmost plot, which is for tetrabromoethane, it turns out that the peak is kind of shifted right to the left side. Okay, any thoughts why it could be? That's because they're of different density, right? If you look at these fluids, for example, aniline has a density of 1.02, okay, which is very much close to that of water, right? However, if you look at tetrabromoethane, the density is 2.97, much denser. Okay, again, that's also evident from the slope, right? If the slope for at least in the initial regime where there is a linear increase, right, the slope is larger for 2.97 because the density difference is more. We know that they should be settling much faster, right, compared to the case where the density difference is very little for the case of aniline, right? This is a plot of, again, drag coefficient as a function of Reynolds number. It appears that for the low Reynolds number cases, okay, for example, Reynolds number from 10 to about 400, okay, roughly, okay, all the data for the droplet seems to be in line with what is expected for solid spheres. Okay, but however, if you go for larger Reynolds number is because larger dimensions, larger size of the droplets. Therefore, you can see a significant change, okay, that you see because that's evident from the upturn of this CD versus Reynolds number plot, right? Again, this is another indication of the fact that the droplets have changed their shape, and one has to worry about such things, when you look at. These are some images from, again, different literature. At the extreme, the plot on the left, again, extreme left case, that's where the droplet continues to remain in the spherical shape during its settling. Okay, however, if you consider a larger droplet, it turns out that that the drops start becoming elongated, right? And this elliptical, the deformation of the droplets leads to droplets being in different shapes. And of course, because of that, your drag forces are going to be very different than what you would see for the spherical particle case, and therefore you would expect that the particles would slow down because of the increase in the drag force. Okay, so in general, the main reasons for the difference between the motion of the liquid drops and that of the rigid spheres is because of the deformation of the drops, okay, which becomes evident when you go for larger sized droplets. Okay, number one. And this deformation can lead to either shape changes or shape oscillations. Okay, if you look at the movies of how these droplets settle, you will see that the drops start going from one shape to the other. Okay, there's going to be drop shape fluctuations which you would have to worry about. Okay, and whenever you have a smooth or a liquid like surface, okay, the flow on the surface as well as flow within the droplets are going to be different. Okay, in the case of solid spheres, I don't have to worry about flow within the particle, right? However, in the case of liquid droplets, there are going to be some internal circulations which can also lead to changes in the way the droplet would behave in a fluid. Okay, so therefore, when you're working with spherical particles or rigid particles of well-defined shape and dimension, okay, things are kind of fairly well laid out. Okay, that means there's a CD versus Reynolds number plot. You should know a little bit about settling regime, the correlation between CD and Reynolds number. All of that is kind of well laid out. You can use those things to understand the settling behavior of solid particles. However, if you go to liquid droplets or bubbles, okay, you'll have to worry about some of these considerations. Okay.